Hi, I'm Norman Wahlberger. The Platonic solids have fascinated mankind for thousands of years. They are very highly symmetrical objects with interesting symmetries, and today we're going to try to get at what those symmetries actually are. How do we describe how this thing actually has symmetries? How do we describe the symmetries of a cube or that of a dodecahedron? Okay, so there are 5 Platonic solids altogether: the tetrahedron, cube, octahedron, icosahedron, and dodecahedron. And they're all highly symmetric, but not exactly as symmetrical as the sphere, which is the most symmetrical of all possible solids. So how do we describe these different types of symmetries? Well, in mathematics, symmetries are described in the language of group theory. And so we're going to naturally be moving towards a little bit of group theory. And traditionally, in three-dimensional space, the standard kinds of symmetries that we often consider are translations, rotations, and reflections. Very simple but relatively common kinds of symmetries. And they have natural algebraic structure because we can compose them. We can do one and then the other. All right, so that's what we want to do, is we want to take one of these solids and ask just what kinds of symmetries does it have? How do we describe them? So at this stage, our Platonic solids are actually physical objects. They're things that we've constructed, that we've made, and we are now staring at them. Now, when we look at something like this, we see a wireframe construction because it's made with a Zohm construction set, which is a very nice way of quickly making one of these things. We can also make a solid object out of a piece of wood, for example, by cutting it with certain planes to make a solid object, and that's how the Platonic solids would originally have been thought about, as being sort of solid objects. So when we think of them as physical solid objects, then it makes sense for us to consider their symmetries also from a physical solid kind of point of view. And in that sense, the most natural kind of symmetry is what's called a rigid motion. So another way of describing such a rigid motion is to say that it's composed of translations and rotations, where a rotation is some kind of thing that you have by having an axis and then moving it around that axis by a certain amount. The axis can be in any direction you like. So that's what a rigid motion is. It's something that transforms our solid without actually changing the essential shape or dimensions. So the rigid motions that we're going to be mostly interested in are rotations. And in three-dimensional space, these are determined by an axis and an angle. Now, we're thinking of these things very physically, and we want to think about having an axis, which is a line in three-dimensional space. And then about that axis, we're rotating. Okay? And the amount that we're rotating is a planar angle. You can think about that in the plane perpendicular to the axis. There's a certain angle of rotation. So we have to talk a little bit about angles here, and this is a little bit of an unconventional approach to angles, but it's quite a nice way of thinking about angles. It's something that I talked about, I think, first in my algebraic topology series. Okay, so we're going to introduce the somewhat sort of obvious idea that when we're talking about an angle, or in the context of a rotation, that there's a natural unit involved. So if we just look at the planar situation, we're thinking about something with centered there, and we're rotating around or moving around by a certain amount. And we want to say, how are we going to measure that amount? Should we measure in terms of degrees or radians or perhaps something else? It might occur to us that there's in fact a natural unit here that's sort of staring us in the face. Because we go like this and we go all the way around, we get back to where we started. That's a natural unit of rotation. It's a natural standardization in the world of angles. We could call that one turn. And so we could talk about fractions of a turn or multiples of a turn in terms of being a turn angle. And we could compare that to the Babylonian angle, so that a turn angle of 0 is the same as a usual angle of theta equals 0 degrees. Theta equals 90 degrees is what we would call a quarter turn. So we'd say that that's a turn angle of a quarter, because we're going a quarter of the way all the way around. 180 degrees is a half turn. 360 degrees is a full turn, a turn of 1. 60 degrees is a turn of 1/6. 72 degrees is a turn of 1/5. 45, a turn of 1/8. 30 degrees, a turn of 1/12. And 120 degrees, a turn of 1/3. Now these are all assuming that we have a sort of positive orientation, so that there is a positive sense in the angle, and then correspondingly the other direction would be a negative sense. So we can also talk about negative 90 degrees being the same as a turn of negative 1/4. Okay, so when we're talking about angles physically, there's a lot to be said about thinking in terms of these natural coordinate systems, much more natural than rather arbitrarily picking 360, and certainly much more natural than arbitrarily having some infinite decimal that we can't compute, like pi, 3.14159 going on to infinity, representing going from here to here. Kind of a crazy system geometrically, isn't it? Right, so we're going to describe things in terms of turn angles like this, and I hope that's not too much of a big adjustment for you. If you want a little bit more experience, you can have a look around in my algebraic topology series, where I talk about how this is quite useful in terms of discussing, well, Euler characteristic of solids and such things. Okay, so we have turn angles, so now let's describe rotations and have a look at symmetries of these objects in terms of how much we're turning about what kind of axes. Okay, so the simplest object is the tetrahedron. So let's have a look at the tetrahedron and ask ourselves, what kind of symmetries does this thing have? So let's put it in a standard position. So let's say there's going to be our standard position. So I'm going to put this triangular face towards you, and this one here is sort of behind, so you should see that somewhere in the middle of that face. And here's sort of a picture of that. So this would be A1, this would be A2 down here, A3, and perhaps A4 back here. Okay, so we have some fixed position of the tetrahedron. And we're interested in how can we move this around in a rigid kind of way, imagining that it's actually a rigid solid body, so that it comes back to this standard position, but possibly with the vertices permuted and the edges and faces permuted. Okay, so the simplest rotation is perhaps one that you wouldn't even think about. It's just the rotation or transformation that doesn't do anything. So that's called the identity. So it's a rotation by 0 about, well, you can choose any axis you want because we're not going to rotate at all. So it's just the transformation that fixes everything. That's still a symmetry, and we're going to include it. Sometimes it's called E for identity. Okay, that's a very special kind of a rotation that we have to include in all of these stories. All right, now let's have a look at rotations about a particular kind of axis. So for example, we could take an axis through the point A1 up here, which is, well, let me put it down here, just like this. So there's the axis. Okay, so it goes through the vertex up here and also through the center of the opposite face. Okay, and if that's the axis of rotation, then we can rotate by 1/3 of a turn. Okay, that was 1/3 of a turn. There's another 1/3 of a turn. There's another 1/3 of a turn. So if I've done 3 of those, I'm back to where I started. So one possible rotation is through a 1/3 of a turn. The other possible rotation is through a 2/3 of a turn, which is all the way like that. And that's the same as simply rotating by 1/3 of a turn in the opposite direction. So a rotation of 2/3 of a turn is the same as rotation of -2/3. So given one of these axes through a vertex and the opposite face, there are then 2 rotations that have that as the axis. So altogether, how many different rotations of that kind are there? Well, there are 4 possible axes, 1 for each of the 4 vertices. So for example, the axis through that point there will be this one here. You could rotate like this, or like this. Okay, so we have 4 possible axes, and for each one of those axes we have 2 possible rotations, either by 1/3 or 2/3. That gives a total of 8 different rotations of that type. But these are not the only kinds of rotations of the tetrahedron. There are also rotations that are determined by edges. So if I take an edge, say this one here, and it has an opposite edge, which is this one down here. Right? So this edge and this edge are opposites. They're not adjacent. So this edge and this edge are adjacent. They meet at a vertex. But this edge and this edge do not meet at a vertex. So we call them opposites. So if I take the midpoint of that edge and the midpoint of the opposite edge, then I can join those 2 midpoints with a line. And that's a line of symmetry. And along that line of symmetry, I can rotate the tetrahedron by exactly a half a turn. Okay, so I've rotated by half a turn. I'll rotate by another half a turn. Here goes another half turn rotation. Back to where we started. Okay. So that's a rotation of 1/2, about an axis through 2 opposite edge midpoints. And so here in this diagram, so there's a midpoint and there's an opposite midpoint, there's the axis, and there's a rotation of exactly half a turn about that axis. So how many rotations are there of that kind? Well, how many of these opposite pairs are there? There's that opposite pair, there's this opposite pair, and there is this opposite pair. After all, there are 6 edges altogether, so there are 3 pairs of opposite edges. And so there will be 3 such rotations by a half turn determined by those 3 pairs of opposite edges. So altogether, now for counting all of the rotations that we've found so far, we have 1 identity, we have 8 of these rotations through an axis determined by a vertex and the opposite face, and we have 3 of these rotations determined by opposite edges, for a total of 1 plus 8 plus 3, which is 12. Altogether we found 12 different rotational symmetries or rigid motions that take the tetrahedron to itself. Now it's very important to understand that there is a simple way of determining beforehand that we would have gotten 12 rigid motions. And that's by thinking about something called a directed edge. Now in this situation here, you see this little red arrow that I've sort of put on this edge near this vertex here, sort of emanating from this vertex. So if we start in this position here and we end up in this position here, the rigid motion is really determined by what's happened to that directed edge, what's happened to this little red arrow. For example, if I know that I'm going to still be in this same configuration, but the red arrow is going to be over here, then there's only one way of arranging things, namely there. Or suppose that I want the red arrow to be up here, then there's only one way of arranging it, and that's like this. So in other words, if I know that the position of the tetrahedron has to be the same position that it started with, and I know the position of the red arrow at the end, then I know exactly what's happened to the whole thing. Right? The red arrow just by itself, this little one-directed edge, completely specifies the relative positions of everything else. So really it's a question of just counting, well, how many possible places are there for this little red arrow? In other words, how many directed edges does the tetrahedron have? And that's actually easy to work out because there are altogether 6 edges, and each edge will have 2 possible directed edges. If we took that edge there, we could put a directed edge emanating from that vertex or from that vertex. So they're all together 6 times 2 or 12 possible directed edges, and so there are 12 possible rotations that take the tetrahedron, move it around, and put it back somewhere in a way that the same volume is being occupied. So this argument doesn't involve a subtle examination of which kinds of rotations there are. we obtain this 12 in a very simple fashion, just by counting the edges and multiplying by 2. And that's how many rotational symmetries this solid has. Okay, so let's have a look at our cube and ask, what are all the rigid motions of a cube? Well, following on from what we were talking about with the tetrahedron, let's count how many directed edges there are. There are altogether 12 edges of the cube, and so 12 times 2 is 24 different directed edges, this being one of them. Okay, the directed edge that starts here and goes in that direction there, sort of say halfway towards the other vertex. There are altogether 24 such possible little arrows that we could put on the various edges of the cube. Let's consider the cube to have this as its standard position. Okay, facing you like this with our little designated special directed edge just along the bottom there. Okay, so every other rigid motion is determined by where this thing goes. So for example, if we want to send this thing up here, then that's the only way of doing it. Now it's along here. Okay, so the rigid motion that goes from here to there is the unique motion that takes this directed edge in this position to the directed edge up here. So there's altogether 24 rotations, and we should be able to count them in terms of what their axes are and what the corresponding turn angles are. So let's do that. The first in our list is going to be the identity, which is the rotation which doesn't do anything. And its axis is not really specified because it's a rotation of 0 about whatever axis you choose. There's one such identity rotation. And now let's have a look at some rotations which are determined by opposite faces. So for example, if I take the center of the bottom face and the center of the top face and join those two with an axis, I get an axis of symmetry of the cube. And now if I rotate the cube about that axis of symmetry, I can do that by having a quarter turn, or I could take a half turn, or I could take a 3/4 turn, which is the same as a negative quarter turn. We're not counting the 0 turn because we've already included that in our list. So the new rotations are about this axis. We have a turn of 1/4, 1/2, or 3/4. And how many such rotations are there? Well, there's going to be 3 for this axis, and then there's going to be 3 for this axis. It's another axis through centers of opposite faces. And then there's going to be 3 for this axis. That's the third axis through the center of opposite faces. So altogether, 3 axes and 3 possible turns or rotations about any one of those axes. So there's altogether 9 rotations of that type. Now there's a bunch of rotations that are determined by edges. So if I take, this edge and look at the midpoints of those two edges, then those two midpoints determine an axis. Okay, and that's also an axis of symmetry, and there's only one rotation about that, namely a rotation of a half a turn. Okay, so half a turn about that rotational axis is a symmetry or rigid motion of our cube. How many such axes are there? Well, there are altogether 12 edges of the cube. And so if we're interested in pairs of opposite edges, there are 6 such pairs of opposite edges. So there's going to be 6 such rotations because each one of those opposite edges is going to determine an axis, and then there's going to be exactly one rotation corresponding to that axis. Now in addition, there's rotations about vertices, or axes that go through opposite vertices. So for example, if I take this vertex here and it's opposite, that determines a different kind of axis of symmetry. And maybe it's a little bit clearer to you what happens there if I tilt this towards you. So if I tilt it towards you, I hope you can see that there's a kind of a threefold symmetry, where there's 3 edges emanating from that vertex there. So there's a rotation of 1/3, or another rotation of 1/3, and then a third rotation of 1/3 gets me back to where I started. So altogether, if we go back to our standard position and our axis like this, there is a rotation of 1/3, which would be like this, or there's a rotation of 2/3, or minus 1/3, which is like this. Okay, so there's two possible such non-zero rotations for each of the axes through turns of 1/3 and 2/3. And there are four such axes. There's that pair of opposite vertices, there's that pair of opposite vertices, there's that pair, and there's that pair. So one for each one of these top vertices, if you like. So altogether 2 times 4, or 8 possible rotations of that kind. We can get that just by spinning the cube like this, another way of getting it. Right? Third of a turn, third of a turn, third of a turn, and we're back to where we started. Okay, so altogether we have one identity, we have 9 rotations about centers of faces, it's like this, spinning it like this. We have 6 rotations which are spinning basically through midpoints of edges, it's like this. And we have 8 rotations which are obtained by taking opposite vertices and spinning by 1/3 or 2/3. For a total of 1 plus 9, that's 10, plus 6, plus 8, makes altogether 24. And that's how many we anticipated there were going to be by just thinking about how many possible directed edges there are for our cube. Okay, so now we come to our favorite Platonic solid, the dodecahedron, which I remind you has 12 pentagonal faces. It has 30 edges and 20 vertices. And if we want to try to put it in something of a standard position, perhaps we could do that like this. Move that around a little bit. Okay, so let me try to put this face here towards you. Okay, so if you're looking at it something like this, then perhaps you will see something that looks a little bit like this. This is supposed to be the face that's towards you with our chosen designated directed edge down there. Okay, so we've said that there are 30 edges altogether. That means there are 60 possible directed edges. That's one of them. There's another one on this side. So number of edges times 2. So there are 60 directed edges. There should be then 60 rigid motions or 60 rotations. So given any other directed edge, there should be a rigid motion that takes this one to that one. So for example, suppose that we want to consider the motion that sends this directed edge to the one that's right here. Okay, so what I do is I just take this thing over here and I move it around so that it's in the position that I want it to be. I think it was something like that. Okay, now it's in the position that it's supposed to be, and the whole solid is occupying the same space that it was before. This is the face towards you. Okay, so there's exactly one rigid motion that takes our designated directed edge down here to any other directed edge. Okay, so let's try to count these rotations sort of more directly in terms of axes and turns. Of course, the rotation of tau equals 0 is the identity rotation. That doesn't do anything, and there's exactly one of those. The next simplest kinds of rotations are the ones associated to faces, or more particularly to pairs of opposite faces. So for example, if I take the face that's facing you there, and there's an opposite face right over here. Okay, so this face and this face are opposite. So if I join the centers of those faces, I have an axis like this. All right, and then about that axis, I can rotate. So I don't really need the axis here. I think you can see what's going to happen. So I'm going to take these two faces here and I'm going to rotate. So rotate by 1/5 of a turn, another 1/5 of a turn, another 1/5 of a turn, another 1/5 of a turn, and another 1/5 of a turn, and I'm back to where I started. So altogether, if I'm going to rotate along a rotation with that as its axis, I can rotate by a turn of 1/5, 2/5, 3/5, or 4/5. There's 4 different kinds of rotations associated to that one particular axis. And how many axes are there? Well, there are 12 faces, and so there are going to be 6 pairs of opposite faces, because every face and its opposite count as one pair. So there's 6 such opposite pairs, so 6 such possible axes that we can use as axes of rotations. So there'll be 6 times 4, or 24 such rotations that are basically rotations about centers of opposite faces. The other kinds of rotations that we've had a look at are corresponding to edges. So if we take an edge, let's say this particular edge right here, just put it in standard position, this particular edge, then it has an opposite edge, namely that one. And we've seen what happens there. We have a look at the associated axis. There's the associated axis. And I can rotate about that axis, but I have to rotate by a half a turn. That's the only thing that will put the thing back in the same position as it started. So I've just rotated by half a turn, and if I rotate by another half a turn, I'm back to where I started. Okay, so there's one non-zero rotation about such an axis. And how many such axes are there? Well, there are 30 edges altogether, so 30 divided by 2 possible different pairs of opposite edges. In other words, 15 possible pairs of opposite edges. So that means that there's altogether 15 such rotations by a half a turn about a pair of opposite edges. And finally, what about through opposite vertices? So if I take this vertex here, its opposite vertex is this one here. Okay. There's also going to be some rotations about that axis. The axis will be like this. Okay. And again, it's perhaps easier if I stick the axis towards you like this. Then you can see that there's a kind of a threefold symmetry around this vertex that's closest to you. So then we can rotate by a third of a turn, and by another third of a turn, and by another third of a turn, we're back to where we started. So given a pair of opposite vertices, now it's in standard position again, there's going to be 2 rotations. One by a third of a turn, and the other by a negative a third of a turn, or 2/3 of a turn. And how many such rotations are there? Well, how many pairs of opposite vertices are there? There's 20 vertices altogether. So 20 divided by 2 pairs of opposite vertices. And each one of those pairs of opposite vertices gives us 2 rotations by a third of a turn and 2/3 of a turn. So we have 2 times 10, or 20 such rotations about axes through opposite vertices. So altogether, we count, we have 1 plus 24, that's 25, plus 15, that's 40, plus 20 is 60. We've accounted for all 60 of the rotations that we decided this solid has to begin with. So naturally we should ask, well, what about the other 2 Platonic solids? What about the octahedron and the icosahedron? Well, it turns out that the symmetries of those are in fact already determined, because the cube and the octahedron are dual, and because the dodecahedron and the icosahedron are dual. And what does that mean? Well, it means that if we join the centers of the faces of one of such a pair, then we get the other pair. So for example, if we take the centers of the faces of the cube, then we get these 6 green dots, and if we join those green dots, we get an octahedron. And similarly, the faces of the octahedron determine a cube. And in the same way, if we take the dodecahedron and we look at the centers of all the faces, then we get 12 new vertices, which form an icosahedron. And then what happens is that any symmetry of the cube will give a symmetry of the octahedron. If you permute the cube so it's in the same position, well, then the octahedron is going to end up being in the same position as well. And similarly, any symmetry of the dodecahedron will generate a corresponding symmetry of this icosahedron formed by the centers of its faces. And it works the other way around. if you have a symmetry of the icosahedron, you can then get a symmetry of the dodecahedron by just doing exactly the same. So in fact, although there are 5 Platonic solids, there really are only 3 groups of symmetries of these 5 Platonic solids. Now in our next video, I want to have a look at these symmetries from a slightly different point of view. I want to look at structures inside the Platonic solids. So it turns out that another way of thinking about what symmetry means is not in terms of transformations. That's only one way. Another way of thinking about things is in terms of sub-objects or configurations contained inside the Platonic solids. That turns out to be quite an interesting story. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.